All right, this is section 10.1.2. We're titling it Randomness and Probability. We've split 10.1 into two parts, so this is the second part, right? So here we go. We're talking about three different types of probability today. All right, and we're going to define each one on this slide. Probabilities that are based on equally likely outcomes are called theoretical probability. This is the type of probability that we talked about yesterday. Examples of theoretical probability are flipping a coin. Because when you flip a coin, the possibility of getting a heads is the same as the possibility of getting a tail, right? Another example is rolling a die. You have the same chance of getting a 1 as you do a 2 as you do a 3, 4, 5, or 6. Pulling a card out of a deck of cards. Every single card has the same chance of being drawn. All of those are examples of theoretical probability where each outcome is equally likely. Probabilities that are based on trials and observations are called experimental probability. And probabilities that are found by calculating a ratio of lengths or areas is called a geometric probability. Today we're going to take a look at an example of experimental probability and an example of geometric probability. Here's our first example, and you can see at the top that this is an experimental probability. Let's understand why. So it says here the number of people who regularly participate in various forms of exercise in a survey of 2,000 people. And we have the table. We have 1,140 people that say that they walk or hike. We have 320 people that weight train, 280 people that run or jog, 240 people that bike, 240 that do aerobics, and 220 that use exercise machines. Now all of this data, all of these numbers, had to be collected. They had to be observed. So the actual action of passing out a survey to people, having them fill it out and give it back to you, and you tallying the results, makes this an experimental probability, right? The possible outcomes of which exercise people do, they're not equally likely, right? Some people are going to do one exercise more than another exercise. And so this is not a theoretical probability. It is an experimental probability. Now, how we find the probabilities is very, very similar from what we did yesterday. We're going to continue to use our basic probability formula. So let's take a look. It says find the probability that a random person participates in part A, weight training. So I'm going to say probability WT for weight training. So we use our basic formula. We're going to find the number of ways to get the desired outcome over the total number of possible outcomes. In this case, the number of ways to get the desired outcome is the number of people that weight train, 320. Over the total number of possible outcomes, well, that's how many people took the survey, right? 2,000. And so we put that 320 over 2,000. And in this case, let's represent our probability as a decimal. So let's throw that into the calculator. We get 0.16. In part B, they ask us to find the probability that a randomly selected person is a runner or a jogger. So I'll say probability run/J. for runner or jogger. So we're going to look at our table. There are 280 people that are runners or joggers over a total of 2,000. Comes out to a probability of 0.14. Let's go to part C. Probability that a person is a biker, B for biker. So we take the number of people that said they were bikers in the survey, 240, over the total of 2,000. And we throw that into the calculator. We get 0.12. And last but not least, probability that somebody is a walker or a hiker. We can see from the table that there were 1,140 people that said they walked or hiked out of the 2,000 people that took the survey. 0.57. Next is our example of a geometric probability. Okay? This question is going to be different from the previous ones, so pay close attention on how to solve it. And I think you'll see as we go why it's called a geometric probability. It says, what is the probability that any two real numbers you select at random between 0 and 6 have a sum that is less than or equal to 5? Okay, so let's understand the problem. We're picking two numbers between 0 and 6 that add up to 5 or less, right? So for example, if we took 0 plus 5, well, that equals 5, right? If we took 1 plus 4, that equals 5. We took 2 plus 3, that equals 5. If we took 1 plus 2, that equals 3, which is less than 5, right? So that would work. There's going to be a whole lot of options here, including decimals. Like if we took 1.2 plus 1.5, that would be 2.7. That's less than 5, right? There are a whole lot of options. That's why there's a graph here. Let's understand the graph. We have a bunch of points. The point right here is the point 0, 5. If we add up 0 plus 5, we get 5, right? The point 1, 4. 1 plus 4 is 5. 2, 3. 2 plus 3 is 5. 3, 2. 3 plus 2 is 5. 4, 1. 4 plus 1 is 5. And 5, 0. 5 plus 0 is 5. Now the reason that this is shaded below our line is because all the numbers below these lines would have a sum that was less than 5. And all the numbers on the line would have a sum that equaled 5. So we are being asked to find what's the probability of picking two numbers between 0 and 6 that have a sum that is equal to or less than 5. Well, we've explained this triangle in the graph is comprised of numbers that have a sum that is equal to 5 or less than 5. But what about the other part of the graph, right? Well, everything in this area of the graph would give us a sum that is greater than 5, right? But still would only include numbers between 0 and 6. Like, for example, they have this point B right here. That point B looks like it's the point 5, 3. Well, 5 plus 3 is 8, right? That's greater than 5. So in order for us to answer the question, finding the probability that the sum of two numbers is less than or equal to 5, we're going to have to find the number of ways to get a sum that is less than or equal to 5 over the total number of possibilities. But we're going to do it by finding the area of the triangle, which we see here, and putting that over the area of the square. Because the area of the triangle represents those numbers that have a sum less than or equal to 5, and the area of the square represents all the possibilities. So we're going to find the area of the triangle. Now you may remember from previous math classes that the area formula for a triangle is 1/2 base times height. And you may remember from previous math classes that the area formula of our square is length times width. So we're going to calculate these two areas, and we're going to come up with our probability. The base of our triangle is 5, and the height of our triangle is 5. So we would have 1/2 5 times 5. The length of our square is 6, and the width of our square is 6. So this would be 6 times 6. Simplify the top and the bottom. So on top, we have 5 times 5, which is 25, times 1/2, which is 12.5. On the bottom, 6 times 6 is 36. Our probability in decimal form comes out to 0.347 repeating. Or as a percentage, since we're used to talking about things in terms of percentages, would be 34.7%. Now what this means is that the triangle makes up 34.7% of the square. And therefore, that's our probability of choosing two numbers that have a sum less than or equal to 5. You can see why it's called a geometric probability, because we had to use some geometry, right? With the areas of the triangle and the square.